The reason is very simple, right? Thermionic emission, it cannot be used for high frequency. Lot of heat would be generated. Not lot of heat will be generated, but actually lot of heat will be required. The temperature which will be required, that will be very high, because high frequency means high energy, isn't it? And high energy means, in thermionic emission, if you remember, the source or the reason for emission of electrons is actually the temperature, or basically the high temperature which you are giving to the cathode material. So for, if you want high frequency electrons to be emitted, you will need high amount of heat also, so that will require very high temperatures. While in the field emission, the reason, or the cause for emission of electrons is actually the electric field. So electric field can be used very high, a very high electric field can also be very can be generated very easily. So that is why for high frequency devices, field emission is more appropriate or more practical in comparison to thermionic emission. Okay, fine. So then, in the previous class, we started the discussion on temperature dependence of conductivity. And as we know, conductivity depends upon two things majorly, which is carrier concentration as well as drift mobility of the carriers. So in the previous class, we started with the dependence of carrier concentration on temperature, right? So that means, and we discussed that there are three specific temperature regimes. One of them is, like, at lower temperatures, all the donor atoms are not ionized. So that is why actually there will be only few donor atoms which will be giving their electrons to the conduction band, and therefore the carrier concentration will be less, and actually it will be a function of this energy difference which is here. Actually it will be exponentially dependent on this energy difference as well as temperature. Then in the medium regime, actually, where all the donor atoms have ionized, they would have donated their electrons to the conduction band, and for this regime actually the concentration of carrier will remain constant, right? The carrier concentration will remain constant in this regime is also known as extrinsic regime. This is the ionization regime, actually, where the ionization is controlling the carrier concentration. Then in the last one, at very high temperatures, that when the temperature is high enough so that the electrons can get excited from the valence band to the conduction band, the carrier concentration will be dominated by this intrinsic electrons, because this is the intrinsic process, right? The electrons coming from valence band to the conduction band. So in this temperature range, the carrier concentration is dominated by the electrons excitation from valence band to the conduction band. So these are three major temperature regimes, and accordingly we can plot this sort of curve, right? At high temperatures, because this is 1 by t, if you can see, this is at high temperature, this is the intrinsic regime where the slope is minus Eg by 2k, because these are the intrinsic electrons, they have to get excited through a energy range of band gap. In the medium range, it is actually constant, the carrier concentration, and then in the final ionization regime, actually it depends exponentially on temperature. Although there is a temperature dependence here also, but exponential dependence is dominating because it is more influential function. Right? So this is what we discussed. Now let us start our discussion on lattice scattering limited mobility. You remember what is lattice scattering limited mobility, right? In the previous chapter, in the second chapter, actually, we discussed that when the source of scattering is actually lattice vibrations, then it is known as lattice scattering limited resistivity. In that case, we discussed, actually here it is mobility, because mobility and resistivity are interrelated, right? So when the scattering is due to the lattice vibrations, then it is lattice scattering limited mobility, and usually it dominates at higher temperature region, because in high temperature regions, the vibrations of the lattice atoms those have sufficient energy to scatter the electrons. At low temperatures they don't have sufficient energy for scattering the electrons. So that is why this process dominates at higher temperatures. So now if you remember, let me, if you remember, mu is equal to E tau by me, right? E tau by me, you know. So if we want here electronic charge as well as effective mass, they don't really, here actually it can be effective mass, they don't depend on the temperature, only tau depends on the temperature. And if you remember in the previous, when we were discussing Matheson's rule, actually when we were discussing lattice scattering limited resistivity, we came up with this expression, 1 upon tau should be is equal to 1 upon su ns, where s is actually the scattering area, u is the velocity or the average velocity of the charge carriers, and ns is the concentration of scattering centers, right? So in this case, scattering centers are nothing but the vibrating atoms. So this ns does not depend on the temperature, isn't it? Ns actually is independent of temperature because it is nothing but atomic concentration, which is actually a property of a material. It does not depend on the temperature. Only this scattering area as well as the velocity, those will depend actually on the temperature. If you remember in this case, for semiconductors, we have already seen that U is equal to 3 by 2 kT. Sorry, U is not equal to 3 by 2 kT. It is actually, just give me a second. It is the kinetic energy, which is kinetic energy is equal to 3 by 2 kT, which means half mu square should be is equal to 3 by 2 kT, which also means that U is proportional to t to the power half or under root t basically, right? U is proportional to under root t. And this scattering area, if you remember, this was actually pi a square, where a square was the radius of the atomic vibrations, right? And this came out to be proportional, directly proportional to the temperature. If you don't remember, you can go back, to the second chapter and you can see how we derived it. But it came out that the this pi a square is actually proportional to the temperature. So now if we put this, all of this into expression for tau, this will be is equal to, there will be some constant of course here, let us say it is a, and then this is t to the power half, and from here it will be t, isn't it? So this means, what does this means? That tau is actually proportional to t to the power minus 3 by 2, right? And if tau is proportional to t to the power minus 3 by 2, mu will also be proportional to t to the power 3 by 2, which is what I have written here, right? Mu L is actually nothing but lattice scattering limited mobility. So that comes out to be proportional to t to the power minus 3 by 2 when actually the scattering is being done by the vibrating atoms. Any questions on this? Any questions? Okay, then let us move ahead. Another type of scattering is actually impurity scattering, right? The impurity atoms. In this case, in case of semiconductors, the impurities will be nothing but the dopants, right? The doping which we are doing for N-type and P-type semiconductors, those will also act as scattering centers. So their the charge carriers, they will be scattered by these impurities. Why that happens actually, that let us say this is a dopant, right? In n-type silicon, we dope it by arsenic, isn't it? And if you remember, arsenic is ionized because electron, the extra electron which is there, it gets, removed from the atom, and then arsenic sits there as a positive ion. And because it is positively charged, the electrons, which will be coming in the neighborhood of this arsenic, they will be scattered, or basically their path will be deviated by the electrostatic interaction which they will be experiencing from this ionized dopant atom, right? So in this case, if we want to define what will be the scattering, the radius, scattering radius, that will be defined actually by this relative comparison of the kinetic energy and potential energy of electron. So kinetic energy is very simple, right? Kinetic energy will be fixed, which is half mv square, and we know that in conduction band, this average kinetic energy will be is equal to 3 by 2 kT, isn't it? When actually this kinetic energy is greater than the potential energy, which is, which the electron will experience from this arsenic atom, then we can say actually that there will be no deviation in the path, because kinetic energy is large enough that the path of the electron will remain the same. But if the kinetic energy is less than the potential energy of the electron, this electrostatic potential energy, when the kinetic energy is less than this potential energy, then the electron will deviate from its original path. And this deviation is nothing but actually the scattering of electron, right? So if we want to define this scattering radius, that will be actually this at this boundary point where actually the kinetic energy is equal to the potential energy. So if we do that, kinetic energy is what? 3 by 2 kT. 3 by 2 kT, that should be is equal to the potential energy. Potential energy is electrostatic potential energy, that will be E square divided by 4 pi epsilon naught epsilon r times RC. RC is this radius, right? From here you can see that RC is actually proportional. RC comes out to be proportional to T to the power minus 1, right? Now the expression for tau remains the same. It will be SU NS. In this case also, this concentration of scattering centers, which is actually the concentration of impurities, that is independent of temperature, or actually that is very weakly dependent on temperature, right? And only scattering radius or the scattering area as well as average velocity, those will be dependent on the temperature. So from here we can put S is actually pi RC square. So this will be T to the power minus 2, and U is proportional to T to the power half, and this will be NS. This will be actually approximate sign here because we are not putting any constants here. So this will be T to the power 3 by 2, isn't it? Divided by NS is actually concentration of impurities, so I will put it Ni. This is what I have written here, right? The impurity scattering limited mobility is proportional to T to the power 3 by 2 divided by concentration of the impurities, right? And this scattering actually dominates at low temperatures, because at low temperatures lattice vibrations don't have enough energy. Their vibrations, the vibrational energy which the atoms have, that is not enough to scatter the electrons, right? Right? So these are the two types of scattering which will define the mobility, or actually the temperature dependence of the mobility. As you can see, at high temperatures, because vibrational scattering is dominating, the mobility will be proportional to T to the power minus 3 by 2, and at lower temperatures the scattering will be dominated by impurity scattering, and that is equal to T to the power 3 by 2 by Ni. So these dependents are actually very different, right? And that is what you can see in the experimental results also. what we see here is, from Matheson's rule we know that, right? From Matheson's rule we can just add the inverse of mobility, and that will give us the effective mobility. Here mu e is actually the effective mobility, and that can be calculated by adding 1 upon mu plus 1 upon mu l. So here in these are the experimental results. On the y-axis we have electron drift mobility, which is plotted on the log scale, and then on the x-axis we have temperature, right? So if you see, let us go one by one. We have plotted only one line for germanium at a very low concentration. The dopant concentration is very low, and here these lines are actually plotted for different concentration of dopants. The red lines are for silicon, and this blue line is for germanium, and this is plotted at a very low dopant concentration. So at low concentration in germanium, the drift mobility is proportional to T to the power minus 3 by 2, as it is dominated by lattice scattering. Okay, so that is very intuitive, right? That at low concentration of impurities, there will not be enough impurities, to scatter the electrons effectively. So in that case, the atomic scattering or the vibrational scattering, lattice scattering, will be dominating. So you will get the temperature dependence from the vibrational scattering, which is T to the power minus 3 by 2. All right. At higher dopant concentration, for example, here let us say Nd is equal to 10 to the power 19 in case of silicon, and low temperature. So in this regime, at the low temperatures, the drift mobility is dominated by impurity scattering, right? Because the atoms don't have the vibrations of atoms, they don't have enough energy to scatter the electrons. So this is dominated by the impurity scattering. Accordingly, we are getting the temperature dependence, which should be 2t to the power 1.5. In these insets, actually, these are the ideal dependence on temperature, depending on lattice scattering or the impurity scattering. So you can see here, at high dopant concentrations at low temperatures, the drift mobility is dominated by the impurity scattering, right? That's why we get the temperature dependence, which is T to the power 1.5. Then at higher temperatures, the vibrational scattering will dominate, right? And we will get the temperature dependence from there, which is T to the power minus 1.5, right? So this is the sort of temperature dependence of drift mobility which we get. One thing actually which I am sort of not mentioning here actually is, in case of germanium, the drift mobility at very low concentration comes out to be T to the power minus 1.5, which is coming from vibrational scattering. In case of silicon, that is not true. Like in experiments, it has been seen actually that for this dependence is actually T to the power. Can you please mute yourself, whoever is there? Yes. So in case of silicon at very low temperatures, this dependence comes out to be T to the power minus 2.5. Why it comes there, actually we cannot, this that is out of scope of our current discussion, because we will have to go into different, like more involved quantum mechanical theories. But for now I just wanted to mention that, because I mean, for silicon and germanium there is a difference at lower dopant concentration. Why it happens, that is out of the scope. We are not going to discuss that, and that is not actually like of our interest for the current discussion. Drift mobility, I mean, this is a very intuitive plot. Like as we increase the dopant concentration, of course there will be more scattering centers, right? And as we increase scattering centers, definitely the drift mobility will decrease, right? After a certain threshold, initially actually if you see, both the hole as well as electron drift mobilities, they remain constant for some time, and after that they start decreasing as we increase the dopant concentration. And this is very intuitive, because we are actually increasing the number of, or the concentration of scattering centers by increasing the impurity concentration, right? So that is why the drift mobility behaves in this way as a function of dopant concentration. Now if we want to look at the conductivity, if you remember, we started all this discussion to see how conductivity of a semiconductor varies with the temperature. And in that discussion, actually, first we discussed how the carrier concentration varies as a function of temperature, and how the drift mobility varies, right? So now let us try to combine both of these two, and see how this defines the temperature dependence of conductivity, right? So if you can see here, the dotted red plot, actually that is the dependence of carrier concentration on temperature. This is the carrier concentration plot of semiconductor, isn't it? This is the log plot, by the way, है ना? The y axis is actually logarithmic scale, and on the x axis we have 1 upon temperature. So this is, we have already seen this red plot, this red dotted line curve, actually red dotted curve, actually this is the dependence of carrier concentration on temperature. And then this green one, this is the dependence of drift mobility on the temperature. Now let us try to examine, and this blue plot is actually the combination of these two. If we combine both the carrier concentration and the drift mobility, we will get conductivity, right? So this is the dependence of electrical conductivity on temperature in a semiconductor. So let us try to see one by one how, what is happening in this region, in the intrinsic region, right? The if you remember, the carrier concentration, that is a exponential function of the the temperature. If you remember, it looked something like n is equal to ncnv. There was some power also, I don't remember. There was some power here. For now we'll just ignore that. And then there was this exponential term, minus eg divided by kt, right? Although the temperature dependence is here also, but that is negligible in comparison to the exponential dependence which is coming from here. And actually that sort of dominates even on the drift mobility temperature dependence, because that is also a, like, direct temperature dependence. The exponential dependence dominates over all these temperature dependence, which is, which are like power dependence. So that is why this curve follows the same trend as, the curve for conductivity follows the same trend as, the carrier concentration curve in this intrinsic regime. Similar thing happens also for ionization, because in ionization also actually we get similar kind of dependence, only instead of eg, which is the band gap, here we have, if you remember, ef minus ec, right? But temperature dependence remains the same, it remains exponential only. So that is why again the conductivity curve follows the carrier concentration curve, because exponential dependence of carrier concentration on temperature dominates in this region, right? Now actually this is the most interesting part, because this is the region where most of the devices function, right? So in this region, if you remember, the carrier concentration remains constant. Actually it is nd, the concentration of dopant, right? In this medium temperature range, the carrier concentration remains constant, and it is approximately is equal to the the concentration of dopants. Because carrier concentration is constant, then of course the temperature dependence comes from the drift mobility, and that is what you can see here in the carrier the electrical conductivity, that sort of gets it bends a little bit in the upward direction to follow this temperature dependence, which is coming from the drift mobility of the charge carriers, because the carrier concentration is actually constant in this regime. So the drift mobility affects the carrier, the drift mobility affects the electrical conductivity only in the extrinsic regime. Rest two regimes, the lower temperature as well as, this is the higher temperature and as well as the lower temperature regimes, they are dominated by the carrier concentration. They are not dominated by the drift mobility. Drift mobility doesn't affect much the temperature dependence in these two regimes. Only in the extrinsic regime, drift mobility, the temperature dependence of drift mobility plays an important role. Okay. you can see in the inset, this is very different from what we get for metals, right? For metals, the resistivity is directly proportional to the temperature. If you remember, rho was is equal to AT, that it is linearly, it varies linearly with temperature. In case of semiconductor, it is not true, right? It is very different, and we get much more complex dependence on temperature, right? Any questions on this discussion? Any questions? Receive the chat box. Okay. If there are no questions, am I moving? Am I going too fast? Are you guys able to understand what I am discussing? Be- Somebody has written yes. That yes is for. Am I going too fast or okay? I am taking that as you are able. Okay, you are able to understand.
Am I audible?
Yes, Varun.
Uh, can you please go to the slides? I think it was of previous lecture. This carrier concentration versus temperature dependence.
Mm-hmm.
Yes, I just wanted to clarify something for myself. Yes, the previous slide. This is the curve that is the dotted curve, red color, right?
Sorry, you're not able to see the screen. I have changed.
Pardon?
I have changed the slide.
Yes. I am able to see the screen. Yes. Can you please go to the previous slide? Just previous slide
This one.
before this curve. Okay, fine. So these are the temperature dependence we have discussed individually for all the three types of semiconductors.
Not three types in the three temperature regimes.
For the for one type semiconductor at three different temperature regimes.
Right, right.
Okay, fine. So then we have discussed that it will be dominated by intrinsic, extrinsic, or thing. Okay, fine.
Okay, okay.
Okay.
Yeah. Okay. Let us go ahead. So now let us introduce a new, I mean, not new concept. Actually, we have already taken this assumption. There can be two types of semiconductors: non-degenerate and degenerate semiconductor. The definition of actually whatever we have discussed so far, actually we have discussed non-degenerate semiconductors. In non-degenerate semiconductors, the concentration of charge carriers, let us say the concentration of electrons is much smaller than the density of states. If you remember, this NC is actually the effective density of states in conduction band, right? In non-degenerate semiconductors, the concentration of charge carriers is much smaller than the effective density of states. And if you remember, this was the main reason actually that we could assume Boltzmann statistics, because we don't need to follow the Pauli's exclusion principle explicitly, and Boltzmann statistics doesn't take into account the Pauli's exclusion principle, right? So these are the non-degenerate semiconductors, because when, if you remember, when we derived mass action law, we assumed Boltzmann statistics, isn't it? So this discussion, whatever we have done, that is for non-degenerate semiconductor. But depending on the doping concentration, because you know that n depends actually on doping concentration, right? So depending on the doping concentration, sometimes the carrier concentration can be in excess. Actually, it can be more than the effective density of states in the conduction band, or the whole concentration can be greater than the effective density of states of valence band, right? Of course, it will depend on the whether it is n type semiconductor or p type semiconductor, right? When that happens, when actually the charge carrier concentration is larger than the density of states, that means there is a practical possibility, or there is a reasonable probability that the electrons can occupy the same states, which is actually not possible, right? According to the Pauli's exclusion principle, it is not possible that the electrons and like the two electrons can occupy the same electronic state, right? So in that case, we need to follow the Fermi-Dirac statistics. We cannot assume Boltzmann statistics anymore for these kind of cases where actually we have excess doping, and because of the excess doping, we have excess concentration of the charge carriers. And actually, these are known as degenerate semiconductors. All right, where the charge concentration is very high. These are known as degenerate semiconductors. As we increase impurity concentration, impurities atoms form a band, right? If you remember, for band formation, that is the requirement, right? There should be a lot of atoms which should be interacting with each other. So when we increase, as we keep on increasing the impurity concentration, their concentration becomes large enough so that they start forming a band actually, okay? And that band starts overlapping with the conduction band and becomes a part of the conduction band. Let us look at here. So usually what will happen is actually, let me draw a figure here. This is my EV, this is the EC, and somewhere in the middle we will have EF, right? When we start doping, there is a dopant energy level which is just below, or very small. This energy gap is very, very small. We have already seen that, right? So this is the ED level. Now what is actually happening is, in this ED level actually there are so many number of atoms that it starts forming a band. As you can see here, actually impurities are forming a band, and this actually band sort of overlaps with the conduction band. Like there are electrons in this whole region, because actually they are coming from the dopant atoms, right? And this band of the impurities, that is overlapping with the conduction band here, right? And most of these states actually, because all the dopant atoms, they have valence electrons, right? So these states are actually occupied. There are Most of these states are actually occupied by the electrons. So what will that mean? That will mean that the Fermi energy has shifted, because if you remember, the definition of Fermi energy is the last occupied energy level, isn't it? So the Fermi energy now gets shifted within the conduction band, which is what is being shown here. Because actually there is this overlap and most of these states are occupied, the Fermi energy level is now falling within the conduction band, right? And this EG, so this EC actually, which was earlier, let us say here, this EC was here, right? Now because this is sort of overlap, the EC will be shifted downwards. Let us say I am denoting it by EC prime. So this EC has shifted, and because of that, this band gap will be narrower, right? Because of that, the band gap will be narrower, isn't it? And this actually overlapping of bands is very similar to the metals, right? So that is the region also that these non-degenerate semiconductors, they behave more or less like metals, because they have very high concentration of valence electrons, and there is this overlapping of the bands. So there are a lot of energy states which are free, and the bands are overlapping as it happens in the metals. So that is why these non-degenerate semiconductors, they behave very much like the metals, and their applications are also like ohmic contacts, which usually metals are used in that. But these degenerate semiconductors, they are also used in ohmic contacts, laser diodes, Zener diodes. These are some of the typical applications of these non-degenerate semiconductors. Okay, in this case the carrier concentration will not be is equal to nd. Why? Can you think about it? Why the carrier concentration will not be is equal to the concentration of the dopants? Because actually this overlapping of the bands and band formation, all the dopant atoms may not be ionized now, because they are forming their own band. So there will be different type of bonding, right, in the within between these impurity atoms itself. So all of these dopant atoms, they may not be ionized. So that is why the carrier concentration will not be equal to the dopant concentration anymore, because carrier concentration comes only from the ionized dopant atoms, right? In this case, all the atoms will not be ionized, all the dopant atoms will not be ionized, because some of them will be forming bonds between themselves. And if they are forming bonds between themselves, then they don't have a extra electron, right? So they will not be ionized, right? So and that is why even mass action law is also not valid. These non-degenerate semiconductors, they don't follow the mass action law. Okay, they don't follow the mass action law. Most of the semiconductor devices, they are actually they use non-degenerate semiconductors. They are actually the as we remember, as I mentioned earlier also, the dopant concentration is very very small, of the order of 1 ppm or less than 10 ppm in most of the cases. But for some certain applications, like I have mentioned here, these kind of semiconductors can also be useful when we do actually excessive doping, and then they start behaving like a metal. These are called the degenerate semiconductors. All right, any questions on this? Again, explain why n is not equal to nd. N is not equal to nd because, see, now the impurity concentration is very very large, right? I mean, there is significant impurity concentration within the semiconductor. Because the concentration is very large, there will be some bond formation happening within the dopant atoms also. Let us say we are doping with arsenic. So now, because the concentration of arsenic atoms is very large, some of the arsenic atoms, they will be also bonding with each other. Earlier, if you remember, we forced that arsenic bonds only with the, let me go back to that slide. If you remember, we forced arsenic atoms to bond only with the silicon atoms by keeping the concentration of arsenic very small, right? If we keep the concentration very small, then arsenic can bond only with these silicon atoms. But let us say if the concentration is larger, and some of one of the neighboring atoms is now arsenic, because the concentration is large, so then they can also form the bonds, right? These two arsenic atoms, they can also form the bonds. And if they start forming the bond, then it is not necessary that arsenic will be ionized, right? Because there may not be extra electron now, because this bond formation will be different from the bond formation of arsenic and silicon. So that is why in this case it is not guaranteed that all the dopant atoms, they will be ionized above a certain temperature also. Okay, there will be only a fraction of electrons. If let me go back, you see, I hope that is clear, right? If n is very small than nc, then band won't be formed in dopant atoms. So how is mass action law is not valid? No, mass action law is valid if n is much smaller than the nc. If n is much smaller than the nc, what does okay, let me just first explain what is nc, nv and n. So n is the concentration of charge carriers. Nc and nv are effective density of states, these quantities. uh, yeah, here you see nc and nv, and these nc and nv actually are effective density of states. NC is actually effective density of states at conduction band edge, and NV is effective density of states at valence band edge. And these the practical implication of these NC and NV actually is that if we assume that all the conduction electrons, let us say all the conduction electrons are at the conduction band edge, they have the energy which is conduct at the conduction band edge, then the effective density of states that will be is equal to this quantity. So it is sort of a measure of the number of states which are available in the conduction band. NC is the number of states or the density of states which is available in the conduction band. NV is the concentration or the density of states which is available in the valence band, right? Now the question is, if N is much smaller than Nc, then band won't be formed in dopant atoms. So how is mass action law not valid? I did not say that actually. If N is much smaller than Nc, then the band formation won't happen, and then the mass action law is valid, because in that case actually we can assume Boltzmann statistics, and as long as we can assume Boltzmann statistics, the mass action law is also valid. All right. Harsh, I hope it is clear.
Sir,
Yes.
sir, it is written that for non-degenerate n is very less than nc, and it is also written that mass action law is not valid for non-degenerate.
Sorry. This is a typing error. I'm sorry. This should be degenerate semiconductor. I'm sorry. I will let me change that immediately. Where was it? It should be degenerate. Mass action law is not valid for degenerate semiconductors. Okay. Any other questions?
Professor Tiwari, uh, we have just now discussed the temperature dependence of conductivity for semiconductors.
Right.
So after this discussion, can we say that whatever we have discussed, that temperature dependence is applicable only for non-degenerate semiconductors?
Right. That's what I said. Whatever we have discussed so far before this, that is only for non-degenerate semiconductors. All the discussion that we have done, that is for non-degenerate semiconductors. Temperature dependence of degenerate semiconductors actually will be very similar to metals. In metals, actually, if you remember, the temperature dependence is actually it is directly proportional to the temperature, the resistivity. Similar sort of thing will be happening in degenerate semiconductors, because they behave more or less like metals. Okay. Any other question? Okay, let me quickly, because there are very simple concept of recombination. I introduced this very briefly earlier also. Recombination is actually nothing but when an electron from conduction band meets a hole in the valence band, and then what happens is actually this, the electron goes into this empty low energy state, right? You can see here the electron in the conduction band, it is combining with the hole in the valence band, and then it is moving, actually it is a transition happens from conduction band to the valence band, and in this process the energy which is released, that comes out in the form of a photon, right? Or it is basically, you will be having a light which will be emitted. Photon is nothing but light, right? So there can be two types of these recombinations. One is direct recombination, another one is indirect recombination. Direct recombination happens when the momentum of conduction band electron is equal to the momentum of valence band hole, because even during all these processes we have to follow all these mechanical principles or quantum mechanical principles, and according to that the energy as well as momentum both should be conserved. right? So if the conduction band electron has the same momentum as valence band hole, then they can simply combine with each other and the momentum conservation will be automatically followed, right? And in that case, the excess energy which is there, that will be released in the form of, let me get my pointer, the excess energy which will be released, that will be in the form of a photon, right? This is called direct recombination. This kind of direct recombination does not happen in elemental semiconductors. By elemental semiconductors, we mean like silicon or germanium, where actually there is only one element in the one element is forming a semiconductor, right? So in these kind of elemental semiconductors, direct recombination is not possible. The reason for that is actually the valence band electronic states, which will follow that kcb is equal to kvb, they lie somewhere in the middle of the conduction band. Actually here they lie somewhere in the middle of the valence band, right, which are fully occupied, right? I mean the density, the states which are in the middle of the valence band, they are fully occupied, isn't it? So there are no states which follow which sort of follow this momentum conservation, and which are also empty. So that is why, and that actually that happens in the elemental semiconductors, and that is why this direct recombination is not possible in the elemental semiconductors. But there are some compound semiconductors like gallium arsenide, indium antimony. These states lie at the top of the valence band. The states which follow this momentum conservation, they lie at the top of the valence band. And this at the top of the valence band, some of the states are actually empty, right? So that is why this kind of direct recombination is possible in compound semiconductors. And that is actually one of the reason, because actually only in direct recombination the extra energy is released in the form of a photon. So these compound semiconductors, they are used in as a LED material, like gallium arsenide. It is used as a LED material because the extra energy after the electron transition from conduction band to the valence band is released in the form of a photon. This photon can be used for lighting purposes, right? This happens only in the direct recombination. Now let us look at the indirect recombination. In elemental semiconductors, recombination happens through recombination centers. Like what happens is, because there are no states which follow the momentum conservation, so what happens is, first electrons actually, they are sort of trapped by these recombination centers. And these recombination centers are basically nothing but localized electronic states just below EC. At the EC energy level, below the EC energy level, there are these empty energy states where the electrons can get localized. By localized, actually in simple terms, you can say that actually that electrons are captured by these recombination centers. When the electrons come in the neighborhood of these recombination centers, they get captured, and then actually the extra momentum which the electron has, it is lost in this recombination center itself, and then actually it is able to combine with one of the photons at the top of the valence band, which will be having now equal momentum. Basically the momentum conservation will be followed because now electron has lost its extra momentum, right? And in this kind of indirect recombination, actually the extra energy is released in the form of phonons. Phonons are actually the lattice vibrations, right? So basically it is sort of heat which will be generated in this kind of indirect recombinations. Usually recombination centers are nothing but acceptor or donor atoms, metallic impurities or crystal defects. These sort of defects or impurities, they can capture the electrons, and then when the electron has lost its extra momentum, it can combine with one of the holes, and then this recombination is possible because now the momentum conservation is followed. But you should remember that the extra energy which is there now with electron, it is released in the form of phonons in this case, not in the form of photons. All right. Phonon is actually heat. So one of the major differences is, in direct recombination, the heat is released in the form of light. Sorry, the extra energy is released in the form of light. In this case, the extra energy is released in the form of heat. All right. Direct recombination happens in compound semiconductors. and they are used, that's why they are used in LED materials. And indirect recombination happens in elemental semiconductors like silicon and germanium. All right. Any questions on this? Why this happens? You remember that the because of the density of states, the like which follow this condition, that happens. Like they are at different places in elemental semiconductors and compound semiconductors. Any questions? If you have any questions, we can take them up in the next class, because I think now already we have, yeah, it is already 10 o'clock. So yes, we if you have any questions regarding recombination, because probably I covered it in a little bit of hurry, we can discuss them. We can start the next class with that, and then we can discuss the next topics. For now, we are keeping the quiz on Thursday. We will see how the situation is, with those students. And are recombination centers a type of energy level? I would say actually recombination centers are sort of defects, like impurities, crystal defects, metallic impurities. All those actually act as recombination centers. They provide an energy level below the conduction band edge. The energy level of these defects is actually below. If you see in this slide, the energy level, where is it? The energy center, sorry, the energy level of these recombination center is just below the conduction band edge, right? Is indirect recombination used anywhere? Actually, it is not a usable phenomena. No, it is not. I mean, at least I am not aware of any application of this kind of indirect recombination. Okay. Maybe you can search for it. Actually, I'm just giving the information from what I have, but you can look online if there are any application of indirect recombination, but I don't think so. Okay. Any other questions? Okay, if there are no other questions, we can stop here for today, and then we'll start in the next class. Yeah, we will discuss more about optical absorption and other concepts. Okay. All right. Thank you very much. We will meet tomorrow.